required instruments and sensors in the control panel.
Objectives.
At the end of this video, you will be able to identify and fix instruments to measure electrical quantities, identify the sensors and fix them on the panel board, measuring instruments used in the control panel. Let us discuss the measuring instruments in the control panel. An electrical control panel is a metallic box that enables the user to mechanically control all electrical devices, appliances, and circuits using electricity. Operators are able to monitor and maintain their entire electrical system. The electrical control panel consists of measuring instruments like ammeters, voltmeters, wattmeters, phase meters, and synchronoscopes. A voltmeter is an instrument used for measuring an electrical potential difference between 2 points in an electric circuit. An ammeter is a measuring device used to measure the electric current in a circuit. Digital panel wattmeter that is ideal for multi-tenant submetering applications like those in residential and industrial environments. A digital electronic voltage meter samples a volt and current thousands of times a second. For each sample, the instantaneous voltage is multiplied by the current of same instant, and the average of its outcome is the real power. Multi-panel meters or digital meters available in single-phase and three-phase versions that display all the basic parameters in each phase like energy, power, power factor, voltage, line and phase, and current at every instant. The instruments are used to measure the electrical quantities, which in turn give feedback on load conditions and performance. If the number of the machines and meter is greater, it is difficult to watch the parameters for individual places. A panel board on which these meters are installed helps collect the data at one place where different machines are working. Sensors used in the control panel. Let us discuss on sensors in control panel. A sensor is a special kind of transducer which is used to generate an input signal to a measurement, instrumentation, or control system. The signal produced by a sensor in an electrical analogy of a physical quantity like acceleration, temperature, pressure, distance, velocity, light, level, etc. Types of sensors. There are two types of sensors: passive sensor, active sensor. Passive sensor. Passive sensors are self-generating sensors that can aggregate a signal without any external power source. Example: photovoltaic cell, thermocouple, piezoelectric device. Active sensor. It requires external power supply to generate the signal. Example: diaphragm used to convert pressure or velocity, oscillations or sound waves into movements of a solid sheet. Classification of sensors. It is mainly divided into two groups. They are digital sensor and analog sensor. Digital sensor. The resolution of the sensor is most accurate and maximum speed. Its ability to detect a change in the sensed quantity is excellent. The output is always taken as 180, high and low, or yes or no. Analog sensor. The resolution of the sensor is less accurate, corporate to digital, and it records very small changes or variations, resulting more errors. Proximity sensors. Without making direct contact, proximity sensors, they are capable of detecting items made of metal, glass, and plastic. These sensors are frequently employed in systems for process automation, automated door opens, and automobile collision avoidance. Pressure sensors. The pressure applied on the surface or item is measured using pressure sensors. They are frequently employed in industries, medicinal, and automotive applications. Electrical sensors. Electrical sensors sense current, voltage, and other quantities and send signals to the inputs of controllers or display screens. Hall effect detection is a common technique used in electrical sensors. Electrical sensors are utilized anywhere information about the condition of an electrical system is required, in anything from railway system to the monitoring of fans, pumps, and heaters. Industrial sensors. A switch often functions in a binary manner, as in on or off, but a sensor is typically intended to provide a variable signal throughout some measuring range. For instance, a level switch can alert a pump to stop running when a tank's design level has been reached. However, a level sensor can detect changes in the tank depth and send signals that can be proportionately displayed on a readout, among other things. Infrared sensors. Infrared sensors make use of a variety of infrared light sources. Some devices pick up the infrared radiation that all objects emit. Others direct infrared beams, which are reflected back to sensors looking for beam breaks. Temperature sensors primarily rely on RTDs or thermistors to measure changes in temperature through the change in electrical resistance that happens in materials. Hall effect phenomena, eddy currents, or capacitive effects are frequently used by non-contacting proximity sensors to identify nearby conductive metals. Additionally, other techniques like optical and laser are employed. Simple on or off proximity switches use the same techniques to detect objects like an open door, or proximity sensors can use to detect little changes in target positions. For instance, ultrasonic sensors can calculate the distance of a tank's contents by timing the transmission and receipt of ultrasonic waves. Strain gauges or piezoelectric sensors are commonly used as force and pressure sensors. Over the linear transducer ranges, these modifications can be calibrated to generate measurements of weight or pressure. Vision sensors use CCD, infrared, or ultraviolet cameras to capture images that can be processed by software to identify faults, read barcodes, etc. Let us collect the instruments and materials required to do this practical. Wire cutter or stripper, 1 number. Hand drilling machine, 6 mm, 1 number. Needle file set of 5, 1 set. Round smooth file, 150 mm, 1 number. Flat smooth file, 150 mm, 1 number. Tachometer digital, 3, 1/2 digital along with tacho generator set, 1 number. Single phase frequency meter digital, 3, 1/2 digit, 1 number. Temperature indicator digital, 3, 1/2 digit along with thermistor sensor unit, 1 number. Voltmeter 0 to 600 volt digital, 1 number. Ampere meter 0 to 30 ampere digital, 3 1/2 digit, 3 numbers. Fixing panel meters and indicators on front panel. Fix panel meters and indicators on floor panel. Identify and select proper range of instruments, voltmeter, ammeter, etc. suitable for this control panel. Identify and select the required sensors for temperature and speed for this control panel. The control devices are fitted on base cover and indicators are to be fitted on front panel. Wiring is terminated in respective points to be connected in the instruments. Proper sockets for terminating sensor outputs are to be provided on the front panel. Mark the positions to fix the indicators on front panel, line indicators, tripling indicators, etc. Make holes for fixing the meters and other fixatures on front panel. Fix the meters and indicators on front panel. Distribution of gadgets on fixing in front panel should be uniform. Proper arrangement and distribution to have a good look on the front panel required. Wire the fitting in front panel using suitable cables. Bunching or typing cables in front panel board is to be done if necessary. Connect the control panel to the earth using a bare copper conductor using a standard wire gauge of 14.
Now let us have a recap of this session. In this session, we have learned to identify and fix instruments to measure electrical quantities, identify the sensors, and fix them on the panel board. Hope this video was useful to you. Thanks for watching. Have a nice day.
Greetings students, in this session of the electrician trade, you will be taught how to regulate the speed of a DC motor with the use of thyristors or a DC drive.
You will be able to use it at the end of this exercise. Read and interpret details of the DC drive nameplates. To operate the load, connect the input and output terminals of the DC drive to the motor. Use a DC drive to control the speed of the engine and operate it with a 1/4, half and 3/4 load. Use the DC drive to reverse the DOR, direction of rotation, and operate the motor at different speeds. Let us take a look at the tools and instruments required to perform DC speed control with thyristors or drives. Tools: insulated combination pliers 150 mm, 1. Screwdriver 200 mm, 1. Connector screwdriver 100 mm, 1. Electrician's knife 100 mm, 1. Round nose plier 150 mm.
1 number.
MC voltmeters 0 to 250 volt.
1 number.
Equipment: DC motor 3 HP 220 volt coupled with DC generator 2 kW 220 volt 1. It's a motor generator set. DC drive 3 HP 220 volt.
1 number.
Materials: PVC, polyvinyl chloride, insulated stranded copper cable 1.5 square millimeter 660 volt 15 meter. PVC insulated flexible cable 14 by 0.2 mm 3 meter. Insulation tape 1. Let us take a look at the preparations for DC motor speed control using thyristors and DC drive. Before starting our exercise, it is advised to do the following elementary things. First of all, you will need to learn the basics of DC motors, their construction and operating characteristics. Understand how to use power electronics, which includes concepts such as rectification, filtering, and voltage regulation. Gain knowledge about thyristor-based or DC drive-based speed control methods. Understand the working principles, circuitry, and control techniques involved in these systems. Get information on the DC motor you are working with, such as its voltage rating, current level, power ratings, and speed, torque characteristics. In order to use your application, you will need an appropriate thyristor or DC drive. Consider the factors that can be considered. Example: voltage and frequency rating, power handling capacity or switching characteristics. Familiarize yourself with troubleshooting techniques for thyristor-based or DC drive system. When handling electrical circuits and high-power equipment, you should be cautious and adhere to safety protocols. You will use the thyristors or DC drive to begin our attempt at speed control of a DC motor.
Our first task is:
read and intercept the nameplate details of DC drive. Note down the nameplate details of the given DC motor in Table 1. Note down the nameplate details of the given DC drive in Table 2. Our second task is to connect the input-output terminals of the DC drive to the DC motor to operate the load. Check and identify the terminals of the DC motor and DC drive. Remove the drive cover. Identify and trace the internal connection. Select the ICTP switch or MCB cables and fuse wire according to the rating of the motor. Draw the circuit diagram and connect the ICTP, MCB, drive and the motor as shown. Connect with main switch or MCB 4 numbers of 500 watt clear lamps fitted in an enclosure having individual on-off facility. Connect double earth independently for the main switch, DC drive and the motor. Check the supply and ensure proper rating of the fuse's main switch according to the motor rating. Our next task is to control the speed by setting the parameter of different load and speed. Select the suitable type of model DC drive with code. Connect miniature circuit breaker MCB, DC drive, MG set and lamp rod. Switch on power supply. Press the on button and measure the speed of the motor by using the tachometer before loading and record the readings in Table 4. Load the motor by 1/4 load by switching on one lamp. Record the current, voltage, frequency and voltage in the load terminal. Vary the speed, observe the readings and record them in Table 4. Load the motor further and switch on another lamp. Total load now 500 watt plus 500 watt, which equals 1000 watt. Record all the readings in Table 4. Load further to 3/4 load, 500 plus 500 plus 500, which equals 1500 watt, and record the reading in Table 4. If the motor maintains the rated frequency after loading 3/4 load, record all readings. Press the off switch once it is over and check the readings you recorded. Remove all the connection and supply cables from the motor and supply. Record your observations. Task 4. Reverse the direction of rotation by using DC drive. Connect the AC supply to the input and output terminals of DC drive when the output terminals are connected to the armature and field the motor without connecting load. Switch on power supply main switch. Press the on key and note the direction of running. Press the reversing key and check the changing of direction of rotation of the DC motor. Show the animation of operating the reverse key and the motor reverse rotation direction. Remember to wait until the motor will obtain stability and then change the DOR. Press the off key to stop the drive. Turn off the main power supply of the DC drive and disconnect the DC drive.
Recap. Let us just recap what you have learned so far. Read and interpret details of the DC drive nameplates to operate the load, connect the inputs and output terminals of the DC drive to the motor. Use DC drive to control the speed of the engine and operate it with a 1/4 the load, half the load, 3/4 the load, full load. Use the DC drive to reverse the direction of rotation and operate the motor at different speeds. I hope you all understand how to regulate the speed of a DC motor using thyristors or a DC drive. Let us meet again in the next session. Thank you students and bye. Greetings students, in this session of the electrician trade, you will be taught how to test, analyze defects and repair voltage stabilizer, emergency lights and UPS.
Objectives. You will be able to use it at the end of this exercise. Read and interpret details of the AC drive nameplates. Connect the AC drive's input and output terminals into an AC motor. Identify the operating buttons on AC drive. Control the motor speed by using AC drive. Use an AC drive to reverse the direction of rotation of a 3-phase induction motor. Let us take a look at the tools that are required to control the speed and reverse the direction of rotation of AC motors by using thyristors or an AC drive. Insulated combination pliers 150 mm 1. Screwdriver 200 mm 1. Connector screwdriver 100 mm 1. Electrician's knife 100 mm 1. Round nose plier 150 mm 1. Equipments or machines. 3-phase induction motor 5 HP 415 volt 1. AC drive 3-phase 415 volt 2 HP 1. Materials. PVC insulated stranded copper cable 1.5 square mm 15 meter. PVC insulated flexible cable 14 by 0.2 mm 2 meter. Insulated tape 1 meter. Fuse wire as required. Let us take a look at the preparations to control the speed and reverse the direction of rotation of the AC motors using thyristors and AC drive. In this exercise, our first task is to connect the input-output terminals of AC drive through AC motor. Ensure safety. Before starting any electrical work, make sure to turn off the power supply and follow proper safety precautions such as wearing protective gear. Identify terminals. Identify the input and output terminals on both the AC drive and the AC motor. Identify and trace the internal circuit of the AC drive. Note down the nameplate details of the given motor and AC drive and enter them in Table 1 and 2. Check the switch or MCB, cables and fuse wire rating and match with motor rating. Draw the connection diagram of ICTP drive motor. Power input connection. Connect the power supply lines to the input terminals of the AC drive. This typically involves connecting the L1, L2 and L3 phases to the respective terminals on the drive. Grounding. Connect double earth independently for the main switch, AC drive and the motor. Motor output connection. Connect the output terminals of the AC drive to the input terminals of the AC motor. Control wiring. Connect any control wires necessary for operations such as start or stop signals or speed control signals according to the specific requirements of your application. This may involve connecting wires from control devices such as a PLC or control panel to the appropriate terminals on the AC drive. Connect the motor, AC drive, main switch as per approved. Check connections. Once all connections are made, double-check all the wiring to ensure proper connections and no loose connections. Make sure all connections are secure and properly insulated. Power up. After verifying the connections, turn on the power supply and power up the AC drive. Check for any error codes or fault indicators on the drive. Our next task is to connect, run the motor and setting the parameter for different speed. Select the suitable type of model AC drive. Connect and wire the AC drive input power supply with terminals RL1, SL2, TL3 when the output terminals UT1, VT2, WT3 are connected to the motor. Switch on the power supply main. Press the run or stop button. The motor will run. Measure the speed of the motor by using the tachometer and record it. RPM, revolutions per minute. Increase and decrease the frequency and check the change in speed of the motor. Press the stop button and turn off main power supply to disconnect the supply. Our next task is to reverse the direction of rotation in AC motor by setting in AC drive. For this process, we should first switch on the power supply main. Now press the run or stop button. Consider the rotation of the motor as forward direction. Set the parameter for the reverse direction. Press run or stop button key. The motor will run in reverse direction. Press the stop button to stop the motor. Turn off the main power supply and disconnect the drive.
Recap. Let us just recap what you have learned so far. Read and interpret details of the DC drive nameplates. Connect the AC drive's input and output terminals into an AC motor. Identify the operating buttons on AC drive. Control the motor speed by using AC drive. Use an AC drive to reverse the direction of a rotation of three-phase induction motor. I hope you all understand how to regulate the speed and reversing the direction of rotation of AC motor using thyristors or AC drive. Let us meet again in the next session. Thank you, students. Bye.
In today's video, we are going to learn how to construct and test a universal motor speed controller using SCR. Objectives. At the end of this video, you will be able to wire a universal motor speed controller circuit on the PCB and test it. Assemble the wired PCB along with the potentiometer and socket in a gang box and test. Test the speed controller with a lamp, fan and electric drilling machine. Check possible minimum and maximum speed adjustments using a contact-type tachometer. Let us collect the tools, materials and components required to do this practice. Trainees toolkit 1 set, electric hand drilling machine 1 number, contact-type tachometer with necessary attachments 1 number, wired lamp holder with lamp of 40 watts 1 number, main operated table fan of any make 1 number, resistors R1 10 kilo ohms 5 watts 1 number, resistor R2 470 ohms plus or minus 5% 1/4 watt 1 number, resistor R3 and R4 1 kilo ohms plus or minus 5% 1/4 watt 2 numbers, potentiometer RV1 1 kilo 1 watts 1 number, capacitors C1 2U2 63 volts 1 number, capacitor C2 100 nanofarad polyester 1 number, SCR C1060 or equivalent or any SCR of 400 volts and current rating greater than 3 amperes 1 number, transistor Q1 DT135 or equivalent 1 number, transistor Q2 DT136 or equivalent 1 number, diode D1 D2 1N4004 2 numbers, PCB board 3 mm into 20 mm 1 number, 100 into 75 mm gang switch and socket used for conduit wiring to mount switch, socket and potentiometer 1 number. Let us discuss how SCR is used to control the speed of a motor. An SCR conducts when a gate pulse is applied to it, just like a diode. It has 4 layers of semiconductors that form 2 structures, namely NPNP or PNPN. In addition, it has 3 junctions labeled J1, J2 and J3 and 3 terminals, anode, cathode and a gate. One of the main applications of SCR is to control the speed of a motor by varying the input voltage to the motor. SCR is like a diode, but with added ability to be able to turn it on and off so that the electricity not only flows in one direction but only flows in the direction when you want there to be a flow. By replacing diodes with SCRs, we can control the average amount of voltage across the motor. Procedure. Step 1. Prepare a PCB for the given dimensions. Check the sizes of the components with the soldering position on the PCB. If necessary, slightly alter the dimensions of the PCB track. Step 2. Check the PCB tracks and clean PCB. Step 3. Test the components to confirm its working conditions. SCR. From the datasheets, identify the anode, cathode and gate terminals. Set the multimeter in resistance mode and place the positive lead of the multimeter on the anode of the SCR and negative lead of the multimeter on the cathode lead. The SCR must exhibit infinite resistance under these circumstances and there won't be a continuous buzzer. According to this test, the SCR is fine if its resistance is high. If the SCR displays continuity, it is short-circuited and faulty. Connect the positive lead of the multimeter to the anode terminal and the negative lead of the multimeter to the cathode of the SCR. Now join the anode to the gate with a wire. There should be no resistance between the anode and the cathode. Zero resistance indicates that the SCR is operating in conducting mode. SCR is OK. Step 4. Wire the speed controller circuit on the PCB referring to the circuit schematic and the PCB layout diagram. Get the wired circuit. Step 5. Make connections for the pot, switch, 5 ampere flush type socket, mains 3-core cable, mains 3-pin top with wired circuit on the PCB by using suitable wires. The wired connection are made is to test the wired speed controller circuit before assembling them in the gang box. Therefore, keep sufficient wire lengths in all connections made for the purpose of safety and ease of testing. Step 6. Test the working of the wired circuit by connecting a test lamp load at the output of the speed controller circuit. Check the lamp glow, bringing the two extreme positions of the speed. If the lamp brightness is not varying, vary the position in the wired circuit or connections. Step 7. Test the speed controller using table fan as load and record your observation. Step 8. Assemble the PCB and other associated items so that the wired speed controller is ready for use. Step 9. Now make connections for the pot, switch, 5A flush type socket, mains 3-core cable, mains 3-pin top with the wired circuit on the PCB by using suitable wires, and test the working of wired circuit by connecting a test table fan at the output of the speed controller circuit. Check the table fan, bringing the two extreme positions of the speed. Step 10. Test the universal motor speed controller unit for its range of speed control by connecting an electric drill gun as load and measuring the speed of the gun at minimum, middle and maximum positions of the speed control pot. Step 11. Use contact type tachometer to measure the speed of electric drill gun at different speed control positions of the pot. The wired and tested universal motor speed controller can be effectively used for any practical applications. So preserve the project work made and use it whenever required. In this video, so far we have discussed wiring a universal motor speed controller circuit on the PCB and testing it. Assemble the wired PCB along with the potentiometer and socket in a gang box and test. Test the speed controller with a lamp, fan and electric drilling machine. Check possible minimum and maximum speed adjustments using a contact type tachometer. I hope after watching this video, you can construct and test a universal motor speed controller using SCR. Thank you and have a good day.
Greetings students! In this session of the electrician trade, you will be taught how to assemble the circuits of voltage stabilizer and UPS.
You will be able to use it at the end of this exercise. Construct a voltage stabilizer circuit on PCB. Test the stabilizer for its low and high voltage cutoff ranges. Assemble on-line UPS with assembled PCB modules or circuit boards. Test the on-line UPS for its function. We are going to look at the tools and instruments required for assembling now. It is circuits of voltage stabilizers and UPS. Tools or instruments. Trainees Toolkit 1. Multimeter 1. AC voltmeter 0 to 300 volt 1. Variac 0 to 300 volt per 1 ampere 1. Materials. General purpose PCB 1. Transistors BC 147 or 157.
2 numbers.
CL100.
2 numbers.
Diode IN 4007.
2 numbers.
Zener diode 6 volt by 0.5 ampere 1. LED red and green 1 each. Inductor 21 SWG standard wire gauge. Ferrite core 100 turns 2. Capacitor A 330 microfarad per 12 volt 3. B 100 microfarad per 12 volt 4. Resistors carbon film half watt. A 1K5, 3K3, 1K, 2 each. B
560 ohms. 2 numbers.
C 4K7, 47K, 3 each. D 1K pot 1. Electronic relay 170 volt to 270 volt bar 6 volt molded type 3 pin 2 each. Buck boost mains transformer 170 volts to 270 volt 1 kVA 1. Assembled modules or PCBs of a on-line UPS 1 set. Incandescent lamps fitted in pendant holders 1. Connecting wires or cables as required. Solder, flux, etc. as required. Let us take a look at the preparations to assemble the voltage stabilizer circuits and UPS. You should start this exercise by designing the circuit and creating a schematic diagram. Determine the required specifications and features for your voltage stabilizer and UPS. Make a list of components needed for the circuits. Common components may include transformers, diodes, capacitors, resistors, voltage regulators, relays, transistors, integrated circuits, ICs, and batteries for the UPS. Make ready with the required components and check for their good condition. Ensure that the components meet the specifications and quality standards necessary for your project. Gather the necessary tools and equipment for the assembly process. This may include soldering iron, wire cutters, pliers, screwdrivers, multimeter, breadboard or PCB, printed circuit board, and a power supply for testing. Set up a clean and well-lit workspace with appropriate safety measures. Ensure you have a stable power source and adequate ventilation for soldering. Gather relevant data sheets, reference guides, and technical documentation for the components you are using. These resources will help you understand the specifications and ensure proper connections. Follow the schematic diagram and start assembling the circuit on a breadboard or PCB. Solder the components on general purpose PCB as per the circuit. Do not fix the transformer on PCB. Connect the wires or cables from the PCB to connect with transformer winding terminals. Finish the wiring and clean the PCB. Check the wiring for its correctness. Begin with the power supply section, voltage regulation and protection circuits. Take note of the polarity of components. Observe proper soldering techniques and avoid solder bridges or cold joints. Connect the transformer input wires to the variac for testing the circuit. Connect the incandescent lamp to the output of the stabilizer. Switch on the supply to variac and slowly increase the voltage till normal LED glow and output lamp glow. Switch off. Remove the lamp and connect the voltmeters. Do not change the variac position. Switch on the supply and note down the voltage in table 1. Test the buck boost action by increasing and decreasing variac voltage. Check the voltmeter initially. It starts to show an increase in voltage but drops to normal voltage. Note down both the voltage in output and voltage at variac terminals. Record in table 1. Reduce the voltage of variac and note the voltmeter reading. The voltmeter voltage will decrease but regain its normal position. In this time, note down the voltage at output and variac terminal voltage in table 1. Remove all connections. Document the circuit design, assembly process and any modifications made during testing. This documentation will be useful for future reference. Let us take a look at the process of assembling the voltage stabilizer and UPS circuits. In this exercise, our next task is to assemble of online UPS using wired PCB modules. Obtain all the required components for the UPS assembly. This includes the wired PCB modules, transformers, capacitors, resistors, diodes, integrated circuits, ICs, connectors and other related parts. Ensure you have the necessary tools such as soldering iron, solder wire, wire cutters, pliers, screwdrivers and a multimeter for testing. Make sure you have a complete list of components based on the UPS design you intend to build. Read through the documentation or user manual provided with the wired PCB modules. Familiarize yourself with the module specifications, pin configurations, and any specific assembly instructions provided by the manufacturer. Set up a clean and well-lit workspace with sufficient room to work on the assembly. Before starting the assembly, plan the layout of the wired PCB modules and other components on the main PCB board or chassis. Follow the guidelines provided in the modules documentation to determine the optimal placement of the modules, connectors and other parts to ensure proper functionality and efficient wiring. Refer to the block diagram and arrange the PCB wired modules. Wire the PCB modules as per the block diagram and check the sequence. Connect the charged battery without shorting the battery terminals. Connect one single pole switch initially with the battery circuit. Connect the input to the EMI filter. Check for any circuit problems. Switch on the circuit of 240 volt AC. After wiring the modules and components, carefully inspect all the connections to ensure they're secure and correctly established. Look for any loose connections, soldering defects, or misplaced wires. Use a multimeter to perform continuity tests and voltage checks to verify the integrity of the connections. Check the output with voltmeters. Record the meter reading in Table 2. Switch on the battery. Check the voltage in the output and record the reading in Table 2. Switch off the 240 volt mains and check the voltage in output. Record the voltage in Table 2. Connect the incandescent lamp in the output. Note the lamp brighten condition while input 240 volt supply switched on and off. Analyze your observations.
Let us just recap what you have learned so far. Construct a voltage stabilizer circuit on PCB. Test the stabilizer for its low and high voltage cutoff ranges. Assemble online UPS with assembled PCB modules or circuit boards. Test the online UPS for its function. I hope you all understand how to assemble the circuits of voltage stabilizer and UPS. Let us meet again in the next session. Thank you students. Bye. Greetings students. In this session of the electrician trade, you will be taught how to prepare an emergency light.
You will be able to use it at the end of this exercise. Assemble the components of the PCB. Construct charging circuit for battery. Assemble inverter circuit for emergency light. Assemble charging circuit and inverter circuit for emergency light. Let us take a look at the tools and instruments required for the preparation of the emergency light. Tools or instruments. Soldering iron 10 watt 240 volt 1. Wire stripper 150 mm 1. Tweezer 150 mm 1. Insulated wire cutter 150 mm 1. Multimeter 1. Materials. Step-down transformer center tapped 240 by 7.50 7.5 volt 2 ampere 1. Rectifier diode in 5402 3.
Lead acid.
Battery 6 volt 10 Ah maintenance free type 1. Toggle switch 2 ampere 240 volt SPST single pole single throw 1. Toggle switch 2 ampere 240 DPST double pole single throw 1. Relay 6 volt DC 5 ampere with 1 NO and 1 NC 1. LED 5 mm green 1. Resistance 1K 1/4 watt 1. Resistance 2.2 K 5 watt 2. Resistance 2.20 1/4 watt 1. Capacitor 10 microfarad 25 volt 1. Capacitor 1000 microfarad 25 volt 1. Soldering flux 10 grams. Soft solder 60% lead and 40% tin 50 grams. General purpose PCB 150 mm by 100 mm 1. PVC insulation tape 20 mm 10 meter 1 roll. Screw type incandescent lamp 6 volt 15 watt 1. Transistor 2N3055 with the heat sink 1. Resistance 50 ohm 5 watt 1. Capacitor 2.2 microfarad 250 volt 1. Inverter transformer 6 volt 20 watt 1. 20 watt tube in suitable sheet metal box 1 set. Silicone grease 5 grams. Let us take a look at the preparations for an emergency light. In this exercise, our first task is to construct charging circuit for an emergency light. First of all, we need to understand the power requirements of your emergency light, such as the voltage and current it needs for charging. According to our requirements, select suitable accessories for constructing charging circuit for emergency light. Draw the circuit diagram of a simple emergency light circuit. Identify and collect each component in the circuit and check for their correctness. Arrange the components except the battery on the PCB to meet the technical requirement and aesthetic sense. Draw the layout of the components of the PCB. Ensure proper polarity while connecting diodes, capacitors, and the battery. Mount the components on the PCB in the respective places. Solder the components. Check the connection as per circuit diagram. Before connecting the battery, double-check the connections to ensure they are correct. Then connect the battery and plug in the power supply. Switch on the AC supply for charging the battery. Use a multimeter to measure the charging voltage and confirm that it remains within the acceptable range for your battery. Check the glow of red LED, which is an indication for the presence of AC supply. Consider incorporating additional safety features like overcharge protection or short circuit protection to prevent damage to the battery and ensure safe operation. After charging the battery, switch off the AC supply. Put on the lamp and observe the functioning of the emergency light, and also check the indicator green LED is on. Our next task is to construct inverter circuit for emergency light. Calculate the power consumption of the light you intend to power with the inverter. This will help you select the appropriate components for your circuit. Trace the circuit diagram of an emergency tube light circuit. Identify each component of the circuit. Solder the components on PCB for making inverter circuits. Mark the inverter circuit board with a charging circuit. Solder the components onto the PCB following the circuit diagram. Be careful to observe proper polarity for diodes and capacitors. Mount the power transistors onto the heatsink and connect them to the PCB. Test the emergency light after connecting fluorescent tube light. Fix permanently the charging unit, inverter, and fluorescent tube suitably in a box or case. Check the indicating LED red and green functioning correctly. Power up the circuit and test its functionality. Use a multimeter and an oscilloscope to measure voltages, current, and waveforms. Check for any issues such as excessive heat or abnormal behavior and troubleshoot accordingly.
Recap. Let us just recap what you have learned so far. Assemble the components on the PCB. Construct charging circuit for battery. Assemble inverter circuit for emergency light. Assemble charging circuit and inverter circuit for emergency light. I hope you all understand how to prepare an emergency light. Let us meet again in the next session. Thank you students, and bye. Greetings students, in this session you will be taught how to assemble circuits of a battery charger and inverter.
You will be able to use it at the end of this exercise. Draw the circuit diagram as per specification. Assemble the battery charging circuit wired on PCB. Do the testing of the circuit wired on PCB. Construct the inverter for the given specification. Do the load testing for the inverter. Let us take a look at the tools and instruments required for assembling circuits of battery charger and inverter. Trainees Toolkit 1 set. Soldering iron 35 watt 250 volt 1. Desoldering gun 65 watt 250 volt 1. Star screwdriver set 1. Ammeter 0 to 10 ampere MC 1. Voltmeter 0 to 50 volt MC 1. Digital multimeter 31 by 2 digits. 1. Equipments or machinery. Auto transformer 0 to 270 volt 5 ampere 1. Step down transformer 240 by 40 volt 300 VA 1. Charger transformer with center tapping 6 volt 0 6 volt 500 milliampere 1. Sealed maintenance free battery 6 volt by 120 Ah 1. Relays double pole 3. Materials or components. PCB 115 general purpose. 2. Push button switches. 2. Toggle switches 250 volt by 6 ampere. 2. Diodes 1N4002. 4. Diodes for bridge 1N112. 4. Capacitors 250 microfarad by 12 volt. 1. Resistors 10 ohm 1 watt 1. Pot 1.5 ohms by 1 watt 1. Low voltage lamp. Pot 1.5 ohms per 10 watt 1. Low voltage lamp 6.3 volt 1. Fuse 250 milliampere 3. Neon lamp 1. Buzzer 250 volt 1. Soldering flux and 60 by 40 solder as required. Diode IN5402 3. LED red and green 1. Transistor 2N3055 1. Resistor 2.2 ohm 22 ohm 50 ohm 1 number each 1K 1 watt 2. Electrolytic capacitors 1000 microfarad by 25 volt 10 microfarad 25 volt 2 numbers each. Capacitor 2.2 microfarad by 250 volt 1. Relay NC or NO 6 volt 1. Transformer 240 volt by 7.50 75 volt 2 ampere 1. Inverter transformer iron core laminated SWG 25 turns primary and 36 SWG 285 turns secondary 1. Fuse 2.5 ampere 0.5 ampere 1 each. SP switches toggle 6 volt 2. Let us take a look at the preparations for assembling circuits for the battery charger and inverter. In this exercise, our first task is to assemble the battery charging circuit. Make sure you have all the necessary components for your battery charging circuit. Typically, you will need components such as resistors, capacitors, diodes, voltage regulators, and possibly an integrated circuit (IC) for more advanced charging circuits. It is crucial to know the specifications of the battery you intend to charge. This includes the battery type, example, lithium-ion, lead-acid, nominal voltage, maximum charging current, and any special requirements or considerations. Adhering to the battery manufacturer's guidelines is essential for safe and efficient charging. Plan and design your battery charging circuit on paper or using circuit design software. Consider the charging method you want to use, such as constant voltage or constant current. Select the appropriate circuit topology accordingly. Select suitable PCB, wired PCB, and other components. Check all components, that is, transformer relays, battery for their good condition. Construct the transformers, relays, and other components on PCB. Connect the charger transformer X1 to the auto transformer X2. Connect the secondary of the charger transformer X1 to the full wave bridge rectifier, which supplies reflected voltage to the battery under charge through ammeter, voltmeter, and potentiometer. Reset switch S4 is used to reset the charger when any fault occurs and the charger is cut off. The switch S1 for on or off. Connect the on or off switch S1 to the input of the AC main supply. Connect the diodes, neon lamps, fuses, capacitor, resistor, buzzer, low voltage lamp in the correct position as in the circuit. Solder all PCB connections neatly and clean the PCB without making any short circuit. Set the auto transformer X2 in 0 level position before charging the battery. Keep the switches S1, S2 and S5 in an open position. Connect the battery to the charger output terminal, positive terminal to the battery positive pole and negative terminal to the battery negative pole, and close the switch S3. Check the readings in voltmeter, which is connected through diode D9 and switch S3. Close the main on-off switch S1 by keeping the zero position of an auto transformer X2, and neon lamp N1 and lamp L1 will indicate on. Vary the setting of the audio transformer slowly from zero position until the voltmeter shows the reading nearer to the voltage of battery to be charged. Switch on the charging switch S2 and increase the voltage by varying the auto transformer till the required charging current, 5 ampere, is displayed by the ammeter. Leave the charger on to charge the battery to the required level. Switch off the buzzer by the switch S5. The error indicator neon lamp N2 and the buzzer stays on till the charger is reset. Press the reset switch S4 only if the process continues once again. Ensure that the circuit components are appropriately sized to handle the charging parameters. Ensure the safety features such as overcurrent or overvoltage protection are included. Task 2. Construct inverter circuit. Calculate the power consumption of the light you intend to power with the inverter. This will help you select the appropriate components for your circuit. Trace the circuit diagram. Identify each component of the circuit. Solder the components on PCB for making inverter circuits. Mark the inverter circuit board with charging circuit. Solder the components onto the PCB following the circuit diagram. Be careful to observe proper polarity for diodes and capacitors. Mount the power transistors onto the heat sinks and connect them to the PCB. Test the emergency light after connecting fluorescent tube light. Power up the circuit and test its functionality. Check the indicating LED, red and green, functioning correctly. Now remove the tube light and make the terminals free. Connect the terminals of mains to the supply and switch on. Check the corresponding LEDs are glowing and measure the output voltage. Connect the inverter circuit with supply. Disconnect the main AC supply and test the output of inverter by connecting load and note down the performance. Use a multimeter and an oscilloscope to measure voltages, currents and waveforms. Check the backup time of the inverter and verify the same with manufacturer's manual. Check for any issues such as excessive heat or abnormal behavior and troubleshoot accordingly.
Recap. Let us just recap what you have learned so far. Draw the circuit diagram as per the specification. Assemble the battery charging circuit wired on PCB. Do the testing of the circuit wired on PCB. Construct the inverter for the given specifications. Do the load testing for the inverter. I hope you all understand how to assemble a battery charger and a inverter circuits. Let us meet again in the next session. Thank you students and bye.
Ladies and gentlemen, so today let us look at a topic in contracts management. One of the more famous mechanism is called arbitration. That's an alternative dispute resolution mechanism. Further, when you speak about a